how this works here, and obviously you'll have gotten the same answers if you did it right. But first thing I should say is this graph, I know you've like had a little bit of familiarity with it already. It is not like two semicircles. When we plot this carefully, we'll see that that's true. Certainly the sine of 0 is 0, and there's a reason we memorize those trig values, or I shouldn't say we memorize them. We know them. We can rederive them if we need to understand them. We can evaluate them, I guess I should say. The sine of pi over 6, for example, is what? All right, I need to assign a scale here. All right, I need you back. All right, so at pi over 6, let's call this a half, and let's call this 1. My scale looks just a little different than yours does out there. So at pi over 6, the sine of pi over 6 is a half, I heard you say. And by the way, thanks guys for not talking. Thank you so much. Sorry for interrupting your conversation. That's my bad. Okay. Pi over 6 is 1. Pi over 4, we get approximately 0.707. I have that up there for a reason. Pi over 3, we get root 3 over 2, which is approximately 0.866. Let's just call that there. Pi over 2, we get sine of pi over 2 is 1. Okay. Now before I go too long, just like kind of computing these, using my trig knowledge from before. Do you understand why the unit circle has like a nice connection to this? Off to the side of your paper, I have the unit circle, and then I have these, what I think are meant to be helpful lines coming across. We're graphing sine, and keep in mind that by sine, I mean, if we think of x, or actually I have it labeled up here as theta. If we think of theta as being an independent variable, right, and we think of theta as being, for the unit circle, the angle that we're sweeping around the unit circle, which intersects the unit circle at a point 1 unit away, then what is sine again? Well, it's really the distance measured vertically above the x-axis, right? Or as we come around, it's the sine distance. Could be negative or positive, right? So what does that come out to be? Well, it just comes out to be the height of the point that's over on the right, on the left side. Well, that'll be the same height you have over here. So do you have that over there? Like whenever I'm using my hand to show you, right? If we have 0 radians, how high is the point off the x-axis? Well, of course, it's got a height of 0. When we're at pi over 6 radians, when we opened up on the unit circle, pi over 6 radians, what's the height of that point? Well, it's got a y-coordinate of 1/2. And as we sweep up, let's keep going up to pi over 2 radians, or 90 degrees. As x approaches pi over 2, y approaches a value of 1, right? So it makes sense that as we draw that line across, we get, do you see why the lines are helpful? I hope you see that, okay. Because normally we don't scale a graph that way. And by the way, I don't have these other labels on there, but do you know that pi over 6 is this line on your graph? I didn't label it, but you can label it. What are these increments then on my graph right now? On the x-axis. Or on your x-axis, the same. What is it? Every, what'd you say? Pi over what? Well, what's each grid line? I didn't have them marked. I have pi over 4 marked. But what are the grid lines at? Yeah, pi over 12, right? Okay, sorry, no one said it like they meant it, so I didn't know whether you actually knew it, okay? All right, so pi over 12, that means the first one, we don't really know what the sign of pi over 12 is off the top of our heads. There's no reason that we can't actually find it, though. We'll teach you how to do that soon, but so it's somewhere in there, I think, though, right? I don't know. All right, so let's keep going. The rest is we can get by symmetry, can't we? We know that the sine of an angle and the sine of its supplement, here are some angles, and here are all of those angles' supplements. Those have the same value. So we can kind of use symmetry to catch these. And the sine of pi, that's pi radians, is 0 again. All right, now we're back down on the x-axis. All right, so, and then we can use symmetry to get the rest of this too. We have 2 pi, we're back home. At 3 pi over 2, we're at -1 down south. And here we have a half, here we have a half, here we have something else. All right, so again, we don't get semicircles. We get these nice, beautiful arcs. All right, The one other thing I'd like to show you is on the calculator here. There's something on the back that you're welcome to try on your own time. But I have it set up for you right now on the calculator. Are you ready for a multimedia extravaganza? Okay.
Yes.
So what I want to make sure you understand what I'm about to show you. Okay. So you don't need to try to reproduce this on the calculator because it's a little bit tricky. It's using a mode that we haven't taught you, and you can play around with it later if you want to dive in. It's called parametric. It's all the instructions are like super detailed in the back. It's just I don't need you to go through it right this second. I just want you to watch the multimedia extravaganza before your eyes. Are you ready? The thing I'm about to plot. Are you listening? The two things I'm about to plot are the unit circle, just like we've just been looking at, with the sine graph, and they're going to be plotted simultaneously. So we've been doing hand exercises recently. It'll look like this, right? Right? So that's what's going to happen simultaneously. Okay, that's hard to do, but we'll make the calculator do it. Are you ready?
Yes.
Watch the two balls and watch that they go. They're always at the exact same height, right? This one's going around a circle. This one here is going like this, but they're always going to be at the same height, just like we just kind of felt, just like we felt as we were graphing this. Are you watching? We're reaching on the unit circle pi over 2. Now we're at pi, and it's a 0. You notice the two balls are always at the same height? And we're coming back home. I'm only graphing one period here, okay? You ready to watch it again? This time, watch it like you mean it, okay? Okay, we've got the unit circle being plotted on the left, and sine x being plotted going out. Do you see them at the same height as they go? Okay, so that should be a nice picture visually of what we just did as we graphed sine on paper 2. So I'm not interested in actually going through the back of that, but you're welcome to on your own time if you want to recreate that experience, if you want to recreate that multimedia experience. Okay, so we have the unique opportunity to introduce to you today Unit 5. Now, I worked hard trying to stitch this back together from 3 photos into a GIF. I use this like, but this was a couple years ago. I was actually thinking about you guys a couple years ago when I was up in Massachusetts on the...
A couple years ago? You've been stalking us our whole life?
Absolutely. I was like, yeah, I'm going to have you guys in class, and I want to be ready.
No, you sounded so excited about it. You're like...
All right. So, yeah, I saw this on the way to a bed and breakfast we were going to up in Massachusetts. I saw it, and I had to stop. I was like, stop the car. We got to get out and take a few pictures. Stitch this into an animated GIF for you guys, and also put this distracting URL at the bottom that makes you think that I made this using some website. Okay. All right. All right, it's not really working anymore, this whole stories I'm spitting for you. Speaking of
Don't watch on the website.
GIF.
No, it's GIF.
The creator of GIF calls it GIF.
But it's hold on. He said that GIF now right in.
GIF is the right way. I'm standing by it. I know G stands for graphical. Graphic. All right, listen. We are starting a new unit today. I didn't realize that pronouncing the word GIF correctly was going to cause such a stir. It's not geographical. Sorry, for the first 20 years of the internet, it was called a GIF, and so I can't switch now. All right. Everyone older than 20 calls it a GIF.
My dad calls it.
Yeah. In fact, actually, that's all there was on the web. It was like the annoying web of the 90s. I had like a GeoCities website that had like animated GIFs on it. Yeah, terrible stuff. Have you made a note already and added them to your Google Calendar and everything? We have a test and a quiz and an IB prop. Surprise, of all surprises.
I can take a picture of it and it automatically set up.
Pop quiz, obviously, as usual. 4 minutes this time around. As you can see in this unit, the first 2 homeworks we're going to get back in our graphing sine and cosine with their transformations game. We're going to get that back on. Hopefully, you guys have, almost all of you have done a little bit of that before. So today and tomorrow will be hopefully just you getting really good at that again. And then we're going to do some modeling. We've got more graphs to do. The name of this unit is graphing trig functions, and their inverses. So maybe you have your graph reciprocal trig functions and their inverses. Well, we'll do that. So hopefully there'll be something for you in this unit. I hope. Okay. We'll try and make it as exciting and riveting as possible. Remember that Unit 4 had the word trig in it. Unit 5 has the word trig in it. Unit 6 has the word trig in it. We're doing all this trig this semester. And then there's more trig for the rest of your life coming too, even if it doesn't have that name in it. Okay. The picture I have here is actually, this is a picture I stole off the internet like everything else. It's a picture of it's a cutaway view of maybe, I don't know, it might be hard for you to tell from where you're sitting, but it's a cutaway view of a sewing machine, actually. Yeah. All right. I know, there should be an animation of that too. All right. Speaking of animations, let's watch another one. This one's going to give you a headache. Let's not watch it too long. And actually, just to spare you, I think what you should do is, just to see the animation I've already kind of showed you today on the calculator, just block your view of these guys over here. And just watch this guy go around in the circle and watch sine. This says y equals sine x. Yeah? All right, good. It's tracking. It's tracking the height of the point as it goes around the circle. This is tracking the height, so that's our sine function. This one here, which function is this down here? If we turn our head like this, this is tracking the distance here, right? It's tracking what? It's tracking the x coordinate of the point, or the horizontal distance, the distance away from the y-axis, and that's producing this graph down here. And if you look at it this way, you'll see it. And what graph is that? Yeah, it's cosine. Here they are in like not headache form. Okay, cool. All right. Sine we've already graphed today. We want to make sure we understand that we can take the sine. We can take the sine of any number. Negative numbers too. We only graphed a little piece of it earlier, just a minute ago. But even numbers that aren't convenient, we can take the sine of. So this is a nice continuous function. It's defined for all reals. Beautiful. Domain is all reals. So we should give a couple highlights of the sine function that, just to remind you of what's going on. It starts with x equals 0, comma, y equals 0. And then it makes a full cycle, which is all we graphed earlier. And we arrive back at the same spot after visiting every possible height at x equals something. At x equals 2 pi, right? And then we'll use the word periodic to describe this repetitive behavior. And once you've done a cycle of 0 to 2 pi, you've done it all, haven't you? Just repeat, copy and paste. The other thing I kind of like about this random graph that I found somewhere is that it has 0 and 2 pi, and it has pi on there and 3 pi over 2 and all those wonderful values. But it also has, do you see it? It also has 2 and 4. It has like numbers on there as well. Because a lot of people are like, do I scale my graph in terms of pies or like in terms of numbers? As if to say that those are different things. All right, but I want to make sure you understand that like 2 pi is a convenience matter for us. But 2 pi, remember, that's still a number. It's still 6.28, and it still belongs on the number line. It's not like some, right? I hope you understand that. So this graph emphasizes that, right? You could call this 2 pi, or you could say the period is 6.28, etc. Right? So sine looks like that, and we'll say more about it as we go. It has maxes and mins at 1 and -1. This is what cosine looks like. It looks almost exactly the same. Why is there the point 0, 1 on this graph? Explain.
Because that's where at the 0, at the pi, or the 2 pi point, it's at 1.
What is it, 1? Yeah, what distance are we measuring?
The 0 degree, or the 300, what is that?
Yeah, Noah, you want to add something? Yeah, if you're looking at the unit circle, right, it's the distance away. The point is 1 unit away from the origin, horizontally. So that's tracking that distance, just remember that. So cosine goes to 0 when we're at pi over 2 and at 3 pi over 2. So it makes sense that it has zeros there and there. And its period is, again, 2 pi. Every 2 pi units, you've captured the entire behavior of the cosine graph as well. And you should just have these kind of burned into your mind after like experiencing this a couple times and thinking about the geometry of the unit circle. The sine graph, you should have one more kind of good in the air hand exercise. Sine x you should practice, right? From your perspective. Here's the origin. Sine, go. Right? This is going to be the next answer, right?
No, I think this is going to be the next.
Cosine, right? Here's the origin. Here's cosine right up above the origin. Okay? Cosine has like a kind of very
that's actually
bird feel. Okay. All right, here we go.
rubbing your head and patting your
All right, just own that, and just do it in the air. Okay, yes. Yeah, definitely. All right. The general form of a sinusoid is one of these two equations. Neither of which should be like a big surprise. Neither of which should be a big surprise to you. We've been doing this since Unit 1 and all your life, right? Not just with sine, cosine, but we might have written A times f of b times x minus h plus k, right? Where it's any function. These letters A, B, H, and K, or sometimes people use A, B, C, and D. They're not new at all, right? They're not even a little bit new. They still do all the same things that you know and love. Yeah?
What is a sinusoid?
A sinusoid is our one big umbrella term for either one of these. Even though this is a cosine curve, we still call it a sinusoid. Yeah, in fact, you were the one that just a second ago, no one else heard you say it, but just made the observation that sine, cosine can be, we could do away with cosine if we wanted, but because then we could shift sine, transform it in a very simple way to create cosine, which is completely and totally true. Yeah. Go ahead. Here. Yeah. So we'll highlight that as we move forward for sure. So you know what the word sinusoid means. What are each of these letters? Okay, so remind me of some of your trig knowledge out there for those who have possibly graphed these before. Start with A. What's A?
It's compression or stretch.
Yeah, the absolute value of A is, well, we should also say that too, right? A for any function is a vertical
Compression or vertical.
dilation on the graph, right? A vertical compression or shrink, expansion.
We don't do stretch.
Stretch or shrink, yeah, stretch or shrink on the graph. Or someone said the trig word, it's the amplitude, right? And really we should say the absolute value of A, yeah, is the amplitude. Here's a picture of various sine curves with various amplitudes. There you go.
You should have played along with it.
How about B? How about B in the language of transformations first? What does B do for any function? If we put f of bx, instead of f of x, we have f of bx. What does that do? Or just remind us. Because that was like a tricky one earlier in the year for some of us. Is a horizontal something, Judah? What is it? Okay, so if we like think about f of 3x, what is that?
F of 3x is x.
Compared to f of x.
Yeah, it's compressed like by a third.
Yeah, exactly. Yep, good job. All right.
There would be 3 segments.
Yeah, so let me ask you this before I actually put up this little formula in a second here. If we have f of 3x instead of f of x, then that's a horizontal shrink by a factor of 1/3 or whatever. So what's the normal period for sine? It's normally 2 pi. It normally repeats its behavior after a space of, on the x-axis from 0 to 2 pi. So if we've just compressed it by a factor of 3, if we've shrunk it by a factor of 1/3, or however you want to say that, then what's its new period? It's 1/3 as big, so 2 pi over 3, right? Or in general, the period will be 2 pi times 1 over b, right? So I just want to make sure, because before I put this up here, I want to make sure you understand that this is not just magic, right?
That was the thing on the test.
Oh, the period. I just obey Mr. Chase. The period is just 2 pi over b. That's what it is. Well, okay, but I mean, you don't need me to tell you that, do you? Like, you don't need to memorize that. It just comes from your understanding of Unit 1, right? It's transformations. That's why. Okay. Or if you want 360 degrees over b. Okay. H and K, I think you know what those do. Remember, those are the horizontal and vertical translations, right? In trig words, you might call h the phase shift. You've probably heard people use that term before. I don't know.
That's horizontal.
You know, to go back and to speak to the people who were saying, hey, cosine, sine are just the same. Yeah, they are actually. They're the same function, 90 degrees, someone might say, and especially engineers love to use the word phase. 90 degrees out of phase, they might say. Sine, cosine are the same function, 90 degrees out of phase. Stay with me, please. Stay with me. The last thing, sometimes people call this the k value instead of the, you could think about it again in terms of transformations as a vertical translation up or down. Y equals k, then we might call the sinusoidal axis, or you could call it the equilibrium point. Where, I mean, there's no, and the reason I say equilibrium is because if you were to bounce a weight on a spring, it would have nice sinusoidal behavior, but in the real world, it would eventually stop, right? Wouldn't it? The place where it would stop would be like at its equilibrium point, at the equilibrium, right? So it would be right on the sinusoidal axis. We've already done this, but I'll put it up here, right? I want to make sure you're clear on this. We have some new words we're laying on top of this. And actually, it's maybe not really new words. It's not like most of you have used these words before. I'm kind of treating you like you've already heard those. And but keep in mind that even if we said nothing about any of these words, you should still have been able to, if you know the graph of sine, and we handed you a really complicated equation, you should still be able to do it, right? Because it's just transformations. You know how to do transformations with any function. If I hand you the function, the parent function. So I'm not too worried about you. Here, let's have some fun with this right here. How do I? All right, I'll click on it. It's okay. I just don't want it to go to Internet Explorer, but I guess, sometimes you have to do that. All right, calm down. I know. Sorry, everybody. All right. All right. Right now I have a picture of sine. I have a picture of sine x right here. We have the point 0, 0, the point pi over 2, the point pi 0, the point 2 pi 0, right? All these points that we love. And now we'd like to do some of these transformations. I'm just going to call on some random people, and you guys are going to give me, you're going to tell me what happens as I change, for starters, A, right? So tell me all the things that A can do, and give me an A value and tell me what it's going to do. How about Rachel? So what does A do, again, transformations-wise? And,
it changes the amplitude to, the vertical stretch.
Okay, so if I let A be 2, what would happen instead of 1?
It would go, up to 2 and down to 2, up to 2 and down to 2.
Is she right? Sure she is. Notice that all the points have changed. What happens to the points on the x-axis? Nothing, right? Which is exactly what we expect with a vertical dilation around the x-axis, right? The x-axis doesn't move. What else can A do, though? Rachel, did you say it? I don't know if you did. What else does A have the power to do?
Huh?
What else does A have the power to do? Besides vertical stretches and shrinks.
Oh, it can flip it, make it negative.
Yeah, so let's do this. Here we go. You ready? Wait for it. Oh, it's so fun. Oh, wait. A is negative. I know. All right. All right, tell me about B. We've already talked about it, but tell me in terms of what's actually going to happen on the graph. Samantha, give me a B value you love, and tell me what the graph is going to do when I produce that new B value. Okay, so give me a B value of your choice. 2, and that'll be, you said that already. Okay. So is she right?
Yes.
I should have actually asked you, where does each of those points move? Well, pi over 2 instead of pi over 2 comma 1, it's now pi over 4 comma 1, just as you expected. And then, of course, we can make b 0.5 as well, in which case this all kind of nicely stretches out as well. Okay. All right. By the way, as we're changing b, the period shrinks. Do you agree? As we make b bigger, the period gets smaller. But there is something, as b gets bigger, there is something that does get bigger, and that's the frequency. Yeah. The frequency is equal to something. Does anyone know a relationship between the frequency and the period? Period per time. Higher frequency, lower rate, lower period. True. Yeah. What's that? B can be negative. Yeah. It wouldn't be very meaningful on this graph. It would be a reflection over the y-axis, right? So I forget if the word frequency comes up. I think it does in one of your homeworks. It's not of a huge concern to us, but let's just leave the frequency. Let's just say it. The frequency is 1 over the period, okay? Or the period is equal to 1 over the frequency, if you've ever heard that, right? So H and K, of course, do what you would expect them to do. H moves this thing left and right. Yeah, okay.
Wait, can you play all four?
K moves this thing up and down. And yes, you can do all 4 at once. There you go. Where did it go? Oh, there you go. Come back.
Wait, can you do all at the same time? I already
Calm down. Oh, whoa, stop.
start them all at the same time.
I just posted it on Google Classroom, so you can play around with it. The link. I just posted that link just now. All right. Calm down. It's exciting, I know. All right. When you're ready, Isabel, why don't you tell us what the amplitude, period, phase shift, and sinusoidal axis is for A. And so what's the period in particular? 2 pi. It's like, since b is 1, it's just, there's no horizontal shrink or stretch, so it's just the normal period. It's just 2 pi, yeah. Good, and we could talk about those in terms of transformations too, but let's just skip, I think we understand what's going on there, so good job. How about Cam for part B, if you can take it? Hitting up the back row today, that's good. All right, Cam.
Okay, so the amplitude is 4, right? Because it's the absolute value.
Yeah.
The period is 4 pi.
4 pi, and why is that? Yeah, so 2 pi over a half, I guess, would be 4 pi. Y'all agree? What else do we need?
The sinusoidal axis is 0, and the phase shift is back to pi.
All right, now we have to be a little careful here. Sorry, Cam. I'm trolling you on this one a little bit. Okay. So the form of the equation I gave you at the beginning is a little different in this one. Right, I wrote it as b times the quantity x minus h, right? So can we massage this into that form? Can we, like, because it's not in that form yet.
So x plus 8.
It's x plus
8.
or alpha plus 8. Do you agree? So then you want to revise your answer, Kim?
Okay, then phase shift is back 8.
Yeah, so left 8 if you're talking about translations and the language of transformations. All right, and then C, so that was a little tricky. That was the hard one. Mateo, you want to take C? Walk us through. Go.
So the amplitude is 3/2.
Okay. Does that correspond to a stretch or a shrink?
That would be a vertical stretch.
Good. Period?
And then
Or whichever order you want to give them to me in.
the sinusoidal axis would be at -4.
Thanks, guys, for not talking while he is. I apologize. Yeah, go ahead. Y equals -4. Sorry, I missed
Yes,
that. Yep.
y equals -4. These 3. The period is 3, and then
Careful, the period is not 3. B is 3, I agree. B is 3. You can think about transformations.
oh wait, no, is the period a third?
A third as big as it normally is, yes.
Yes.
And
So
it's normally
pi over 3, or 2 pi over
2 pi over 3. It's normally 2 pi, but now it's a third as big. So 2 pi over 3 is the period. And the phase shift.
The phase shift is 30.
Yeah, there is none. All right. Good. All right, so again, we can talk about transformations here as well. Like if you were doing B, we'd need to also say, notice that this hasn't been picked up at all as we're doing B. But if you were to go to graph it, you would also want to maybe take into account what transformation that isn't captured in this little list. Part B. There's one transformation that kind of isn't mentioned really here. Yeah, the flip over the x-axis we'd have to be very mindful of. The fact that it's cosine rather than sine we'd have to be mindful of. Like this doesn't give us everything, right? But it is kind of a critical list of information. All right, so let's actually try graph one now. Starting nice and easy here with just 2 things happening, not all 4 things happening at once. Yes. All right, so, and by the way, we're just going to do as many problems as we can, and tomorrow we're going to be working on this too. So the homework 1 and 2 are both on graphing sine, cosine, and the transformation. Get you back in shape on rest. All right, what's the amplitude? 3. And there's a reflection, yeah. And what's the period? It's just pi. All right, so I think I'm ready to go here. Okay. So I'm putting this here. This is not a horizontal asymptote, even though I know we've used the dashed line for that before. 3 we'll put up here. I'm going to put this. This is kind of like bounding where my cosine graph is going to live. Okay. This is in the middle, the sinusoidal axis. Y equals 0 is what it still is. And then we know that maximums and minimums will occur at y equals 3 and y equals -3, the amplitude. Tells us that. Okay. And then what I really would like in my life is 1 point on the graph, which is not too tall an order. Does someone have one? 0 is go for the low-hanging fruit. 0 comma something would be a great point to get.
I2.
So 0 comma -3. And how did you come up with that? Well, you could plug it in, right, and actually get -3, right? Does that work? 2 times 0 is 0. Cosine of 0 is 1 times -3 is -3. Or you could think also about transformations. I know that cosine normally has the point 0, 1 on it. And this graph has been stretched vertically by a factor of 3 and reflected over the x-axis. So one way or another, we should confirm that. The beautiful, wonderful, powerful thing about graphing trig functions is every time you plot a point, you simultaneously also graph an infinite number of them, don't you? Because of the periodic behavior. I mean, there are not too many other graphs we've created where like every time you come up with a point in the graph, you also get an infinite number of other ones. That's pretty powerful. And where do they occur? When's the next time? I mean, there's another time, it's periodic, that this value will be -3, and it'll be pi units later on this graph. So I'm ready to assign a scale. I've already assigned the scale of my y-axis. What's the scale for my x-axis? What do you want to make it? How about we make it so that we can label pi over 4 or pi over 2 and 3 pi over 4 easily somehow? That would be nice. We kind of know there are 5 key points on our graph. So at pi, we get another value. At 2 pi, it's going to come back home again down there at 5 pi over 2, down here at negative pi, negative 2 pi, negative 5 pi over 2.
And then halfway in between them, they'll be at the middle.
Yeah, and then now, okay, so then what, that's the question, is what happens here at pi over 2?
It's at 0. Yeah.
Well, yeah, we could actually check pi over 2. If you plug x equals pi over 2 into the original, 2 times pi over 2 is pi. Cosine of pi is, what's cosine of pi? Negative 1 times negative 3 is positive 3. Yeah. All right. Or we just know it's halfway in between these two minimum values will be this maximum value, right? We can just use the symmetry to get this. In fact, what's the value at pi over 4? Yeah, and we can also check that. If you plug pi over 4 in, you will get 0.
That's because it's 1 period, right?
But, I mean, really, once we've laid down those first 2 points, we're kind of done, right? The other ones we just get halfway, quarter of the way. We're kind of done. These 5 points are critical. Once we have those, we just copy and paste, right? If you want to do a couple periods just for fun, we can. And then this is important too, that you practice your drawing skills. Okay. I was set up for success here, but I decided that 2 periods is all you needed. You can keep going if you like, though. All right. 2 periods is definitely cool. Yeah. I'll sometimes be more specific with the instructions. You should always get at least probably 1 period, though, right? I would think. All right, here's one more for you. I think we can do this one for sure before you go. Maybe even see how far we get. Please prove to me that you can do another one. Again, we're only doing 2 little things right now. 2 things right now. We haven't thrown all 4 things at you yet. I got the amplitude for you if you want it. That's nice. That's nice of me. Yeah, you're welcome. You're welcome. Have a discussion with your friends about what the period is.
Whatever that is. What's it called again? Yeah, 4.
What's the period? Figure it out. What'd you get for the period?
4.
Yeah, 2 pi over 2 is what b is. So yeah, that comes out to 4. You feeling that? So I kind of like that. We'll call 300 right here. How about? And negative 300 here. Sinusoidal axis is still, we haven't moved it yet today. Y equals 0. 300. Beautiful. And then we'll call that 4. How about? We'll call that 2. We'll call that 1 and 3. Oops. I failed. All right. How'd you do? All right. Not a huge amount of pressure yet. Like once we throw all 4 things in, these can be a little bit of a headache sometimes with all 4. But so far, I think we're like doing pretty well. The scale is not super hard to reason with. So we'll do some more tomorrow. That's a very convenient place to stop. Are you getting your head around you again about how to graph sine, cosine, and transformations? We just want you to kind of get tricky with it, you know? Like,
I said that earlier. No one heard me.
oh, I got it. Okay.
Trigger with it, guys.